aspects of diversity in planktonic foraminifera through time. So in this talk, I'm going to be focusing on one particular measure of diversity that is unique to forams, really. And what this is trying to describe is what is the average community age of the species that we're finding in the assemblage. So if you have a set of species, and you then measure the age of the species on this phylogeny. So phylogeny of forams, age back in time, 60 million years ago, and here's the different species that are still extant. And this phylogeny was created using fossils, and so we've got relationships that you can see when they speciate in time. We've got a good enough fossil record that you can actually put quite accurate datings on when these splits occurred. So instead of having a molecular phylogeny where you can only date sister species separations, we can see when the present day species separated from species that are now extinct. So here we have an old assemblage that's made up of old species. If we have a young assemblage, then it is made up of much younger species. And the average community age is the abundance weighted, so how many individuals do we have, times by the age of those individuals. So what you're measuring is what is the average age of an individual in a community. So when you have an older community age, that suggests that a community is made up of species that have evolved a long time ago, whereas a younger community age implies that your species have evolved relatively recently. And this is helping to give us some information on how the species in that community is structured, whether they are relatively young or relatively old. So what are planktonic foraminifera, having just talked about them? They are ocean plankton, they are unicellular, and they float passively in the oceans. You can see, scale by here, they're up to 1 millimetre, but very small, and their skeleton is calcareous, which means that they're preserved in the ocean sediments. And so, if we want to study them through time, you drill a hole in the bottom of the ocean at basically any point across the world, and you'll be able to bring up forams. And they are so abundant that we can get community information as well as just, so at each site you can say these are the species that are present and these are their relative abundances. So here you have your ship that drills its hole down, ocean sediment, and the difference between this sort of community or assemblage information compared to what you would get if you just sample on the land in one site is that we're averaging in the bottom differences in, so multiple zones in the ocean. You might get different species living at different depths, and you might get different species in summer or winter as you have different ocean structures. So these all collapse down into one community in the base. But so you're looking more at a time averaged assemblage. So the aims of this study were to consider the distribution of community age in the present day, so where the species, what are the ages of the species today, how does this correlate with the environments that we see today, and how does community age change when we have changing environments. So in this case I'm focusing on the Eocene, which is a change from a warm to a colder world. So for the present day, we have a data set of points taken from across the world's oceans. There's about 2,000 points in here, and you can see a very good range of latitude and spread, quite a good range of longitude. There's a couple of sites where we don't, or regions of the oceans you don't get data, and that is because in those places the bottom water is acidic, so the calcium shells are dissolved. So you don't get many forams preserved here, or you don't get the complete community, you will have lost some. So we've excluded sites where that is likely to have occurred. So if we look at what the community age is like in the recent, you can see here's our colour scale on the left, that these average age is 5 million years, at the top the average age is 35 million years. And you can see there's, most things are somewhere in the middle, so between about 10 and 25. You get very young species at very high latitudes, and this is a site that's dominated by one particular species that evolved recently. If we come a bit further south, you get a much older community. So here, in the subpolar regions and down along here, we're getting a much older community age. You're also getting quite old in Indian upwelling and in this equatorial region. You get younger ages in the upwelling off the African coast here and further up there, and also in the Pacific upwelling. So there seems to be a link between some sort of latitudinal variations and community age. So if we consider what correlates with this, we have a range of environmental measures, and these are taken as the measures for the last 5 to 10 years, average, taken from climate data, satellite data. So information like sea surface temperature, variations in salinity and temperature through the year, the average salinity, productivity, all these factors have been suggested to be linked to foram diversity. And if you do an equivalence measure of the richness, so to speak, number of species that are found, which are not shown here, you get a very strong correlation between these variables. Your R squared goes up to about 0.9%. So community age, there are correlations. It looks like temperature is the main driver of community age, so temperature, which is correlated with latitude, is obviously highly important. Stability is also coming out as significant. So this is the longer these bars are, the more significant that variable is. And you'll notice the R squared is now 0.54, so it suggests that although environmental variables are correlated with this, other factors are also important. So potentially the historical information is also contributing to our community age. And if we just focus on temperature, which is the main variable, we can see what this relationship is between temperature and community age. And so here we have low temperatures, here we have high temperatures, and this is a relatively older community and a relatively younger community. So you find that really low temperatures, we're getting young communities. That then goes to a peak in the middle, and then a dip again up to a slight peak. And the three different colours you see on this map are showing the three different oceans. So there's similar relationships in the oceans, though they vary a bit. So if we then use those environmental variables to predict what the community age is across the oceans, you can see the same sort of patterns we were noticing earlier. So the older ages in the subpolar latitudes, older ages in Indian upwelling, younger ages in African upwelling and in the Pacific. And so there seems to be a relationship between the latitude and the age, and the expectation is those environments that are more that have persisted for longer and are harder to live in. So subpolar regions are less stable, and there's more seasonality. It looks like such sites, once an individual has evolved to live in that environment, other species find it hard to invade. So those communities are dominated by species that evolved a long time ago, and new species can't come in. Whereas in other regions, that down here, it looks like we've got new species are able to come in all the time. It's much less driven by, it's much less limited, it's much easier for new species to come in. So if we then go look back in time, I'm focusing now on the Eocene. So this is the time from 55 to 34 million years ago. On the stats, we have here the temperature. So you can see that at the early Eocene, it was as hot as it has been in the Cenozoic. By the end of the Eocene, we've got a temperature gradient decreasing, so ice is starting to form on the poles. So through this time, we've got a development of a temperature gradient, and if temperature is the main driver of diversity, you'd expect that to have some impact on our observed community age. So the Eocene data set is not as complete because it's harder to obtain information from the Eocene, but we still have a good range of latitudes and longitudes. And in the graphs I'm going to show you, I've collapsed the latitude down, so instead of looking at longitudinal variation and latitudinal variation, we're just focusing on the latitudinal variation. So if we look at what the relationship is in the recent, you get the very high latitude young, and then the much older ages at slightly lower latitudes, and again the much of the older ages at the equatorial regions. So through the Eocene, here we've got latitude against average age. In the early Eocene, there is no difference in community age with latitude. You wouldn't expect to be able to get older species, so the fact there's nothing up here is because this clade evolved 65 million years ago, and we're now looking sort of 40 million years ago, so you can't get anything older than about 15 million years. But there is no change in community age with time, so the species seem to be able to speciate at any latitude. As we move to the Middle Eocene, you start to get older ages at high latitudes, but not at low latitudes. And by the late Eocene, this pattern is more pronounced, so we're getting older species up here and younger species down here. And so if we look at a simple linear correlation, as expected, through the early Eocene there is no obvious relationship between latitude and age, and by the middle to late Eocene we're getting older ages at higher latitudes and younger ages at lower latitudes. So that's kind of suggesting that maybe in these higher latitudes species are less able to speciate in that environment. So the species is dominated by those that first evolved, and other species are not able to invade. Whereas in younger latitudes, we've still got a relatively young species age, so it's suggesting that new species are evolving into that environment. So concluding, forams are an ideal group in which to study this. You can't do this sort of measure of community age in anything other than a species with an excellent fossil phylogeny, because we don't have the information from molecular phylogenies in which to look at community age. And the subpolar regions in the gyres, so those regions that are more stable, seem to contain the older communities. They seem to be dominated by sites where we haven't had new species coming in. They are full of older species, and new species are not able to speciate into it. And through the Eocene, the high latitude communities became older, while the lower latitude communities were staying much younger. So we've got the development of the pattern like we see in the recent. It developed through the Eocene. So thank you for listening.